Hello and welcome to today's presentation of image engineering. We will talk about the challenges that usually arise when testing camera systems, especially of high dynamic range systems from the automotive sector. My name is Max Gede. I'm your presenter today. I'm a research and development engineer at Image Engineering, and I'm responsible for various development projects which are mostly related to the automotive environment. So in my 7 years at Image Engineering, I gained a lot of experience in measuring imaging systems, and a lot of this experience goes back to the time at lab when I was trying to get the maximum out of the available equipment, the measurement equipment. When working with automotive-grade HDR cameras or high dynamic range cameras, we are often faced with challenges, and some of them can only be solved with the right methods and with the right hardware. So today we will cover a range of the challenges, from the most basic to some unique, more typical for the automotive sector, like dealing with extremely short exposure times, for example. Let's start by looking at an image. So what do we see here? This is an image of a street scene with vehicles, cyclists, pedestrians. There's a road in it, and the contrast of this image is quite small. To be precise, it's exactly 0. No matter how calculated, Weber, Michelson difference contrast, it is 0. I changed the original image so that the contrast is 0. So we can see that we don't see anything, as the amount of information in this image is also 0. It is completely uniform. So we could say contrast allows an imaging system to show an object. Now let's take a look at the image as it came out of the camera system. Now that the contrast is no longer 0, it's higher. Objects in the image can be detected. Usually when transferring contrasts from the scene to a camera, the contrast is not transferred to the same extent. As you can see here, for example, it is clear to see that some contrast from the scene is lost, but in the imaging system, but it is still preserved to detect. It's still preserved enough so we can detect the cycling lane. Looking at the car, on the other hand, on the other side of the image, we can see that there is a major loss of contrast. It goes to this extent where the whole car is just one uniform plane. Finding out about such issues involves a lot of testing, and field testing is a major, when not the major, cost driver in the development of ADAS systems. So one way to reduce these costs is to move some of the road testing to the lab. And here we come to the first challenge on our way: how to replicate real-world contrasts in a lab environment. Okay, let's begin with a uniform light source. In our example, the new VEGA light source from Image Engineering. It is a direct current LED light source and a comparatively small footprint. And sizes often are difficult to get across in illustrations. So we are speaking of a cube with an edge length of 12 centimeters. So it's pretty small. As you have seen on the front of the image is a uniform target, and now we can just swap the uniform diffuser for a gray step chart like this one. What you see on the left side is a simple gray wedge. It is equipped with equidistant step side patches, equidistant in the optical density domain. And this particular layout we use to analyze for P2020 image quality factors. something like contrast detection probability, CDP, or modulation light mitigation probability, which is MMP. If you're not familiar with MMP, I suggest visiting the, if you're not familiar with P2020, I suggest visiting their website. I will show a link in the slides. P2020 is a working group of the IEEE Standard Association, and their main focus lays on the development of an image quality standard, which is meaningful for the automotive industry in this case. So maybe a short example on how a possible measurement could look like to solve our challenge. In the usual case, the camera, just like the light source, can be controlled by a computer. In the best case, even both can be automated together. So the light source, let's take a look at the outputs of both systems. The light source is our scene in this case. So it is our scene and it's simultaneously the input for our imaging system. Let's take a look what happens with the image if it goes, or what happens with our input if it goes for the imaging system. Okay, this is exactly why we wanted to test in the first place. Even without further investigation, we can see that there are major issues going on here. Different systems show different behavior in this case, and we can see there are some different issues we can see here. For example, on the left side, this example, we see there is an unexpected increase of noise in the top left corner where it gets bright. You would not usually expect it from a single exposure image, something like this, but HDR images often introduce such behavior or such artifacts. The both examples in the middle and on the right, we see there is also an increase in noise, and there is a very strong reduce in contrast, which we can see here. And loss in contrast may be translated to loss in detection. So let's take a look at our next challenge. It's how to create a variety of luminances in a lab. Usually you just dim your light source, but dimming a light source introduces different challenges again. And dimming light sources, for example, with tungsten or with LEDs, introduces color shifts. And this might become an issue with testing. So what you can do is with VEGA, as it is a stabilized light source, and we talk about color shifts later, you can dim your light source without hesitation, and you can achieve a high variety of luminances in your testing. So, for example, we can take a look. We can, or VEGA light source has a dynamic, linear dynamic contrast of 1 million to 1, so it's about 120 dB. And it's just a light source. So if you control your light source and on top you put a target with 20 dB dynamic range, you would increase to 140. And you can even create different targets, so customized targets on the VEGA and increase the overall dynamic range even more. But looking at this example, we can take samples at lower luminances, we can dim the light source higher and higher and higher, and we can dim the light source without introducing color shifts or any other issues. Okay, how to simulate a high scene dynamic range. For some cameras, it is not enough to capture high contrast between two images to test for issues. It is also interesting to take a look what happens if the camera is introduced to a really high dynamic range scene. So what we can do here is we just introduce more light sources. And in the case of VEGA, we have a controller which supports up to 7 light sources, which can all be controlled individually, but they also can be controlled in small groups and or controlled even as one big group with 7 light sources. And they can be placed, as they are really small, they can be placed anywhere in your field of view of the camera. So, to go back to our test, we extend the dynamic range just by extending or multiplying the light sources, or introducing multiple light sources. How to measure short exposure times? HDR cameras tend to have extremely short exposure times, from time to time even moving down to 10 microseconds or even lower. And I don't want to go through the math exactly, but if you are using a pulse width modulated control light source, you can calculate the effect of the pulse width modulated light source on your image material. And the shorter the exposure time of your camera is, the greater is the impact on your image or on your exposure. And this inaccuracy can be calculated with this equation here. And what this equation basically says is we want to have a ratio between our brightest exposure and our darkest exposure. And the brightest exposure will be with n pulses plus 1, and the brightest exposure will be with n pulses. As you can see in the presentation on the bottom of the slide, this is exactly what happens. From time to time, the worst case is we have one capture where we get 5 pulses, and we have one capture where we get 4 pulses. And this works for every pulse exposure time configuration. If you map these inaccuracies on a map, so on the x-axis we can see the camera exposure time, and on the y-axis the worst case inaccuracy. You can see that even that the most interesting area between 10 microseconds and 1000 microseconds is strongly affected by PWM light sources. So, if using extremely short exposure times and working with HDR cameras, the only solution is use DC-driven and not modulated light sources. Challenge 5. How to simulate flickering light sources. Now that we get rid of the flicker in our light source, we want to introduce flicker, but we want to introduce it in a controlled way. Why is it important, you would ask? And here is a good example. I will just slow down a little bit more so we can see. There is a complete loss of information in many consecutive frames. So the camera is blind in the spot where it needs to see the sign. And this is not even the worst example. It is thinkable of that a camera might be completely blind when introduced into an environment where a flickering light source is a major light source. And we can reproduce this behavior with our light sources. I have some examples. We can see here. We can introduce flicker to our light source and see the effects and also evaluate the effects afterwards. So the light source is capable of simulating flicker. It's simulating of LED flicker with a wide variety of frequencies, duty cycles, and what's most important, also phase shifts. Because you're not always sure you will get the phase. You never know which phase you are starting with when testing. And yeah, so the frequency range is 1 to 1000 hertz, and we can examine with 1 to 99% duty cycle. Very important also is that the VEGA is capable of simulating sinusoidal flicker. So we can introduce sinusoidal flicker with a frequency range of 10 to 500 Hertz. And for the most experimental approaches, we can also generate a triangle signal with 10 to 500 Hertz. So the last of our challenges is how to reach high measurement accuracy. And the 3 points I want to show you are spatial uniformity, temporal stability, and color stability also. I'll come back to it later. So if you want to reduce the influence of the light source on your measurement, you have to have a most uniform spatial light source. In the case of the VEGA, it is 95% over the whole output window. So going down to each patch, it is much higher. And the deviation of intensity output when warmed up is much less than 1%. Talking about the spectral stability, the usually used LEDs are unstabilized, and let me start with this slide again. So usually LEDs show a chromatic shift with changing temperature. And to encounter this, VEGA is stabilized and operates in a very small temperature range. And the deviation of the chromaticity of VEGA is well within 1,000th of x prime y prime. So thus also solving our challenge of high accuracy measurements. So summarizing, VEGA is a direct current LED light source. It has a very high dynamic range, 120 dB only for light source without any targets. Speaking of targets, which are customizable to increase even the dynamic range even further. And it provides a high temporal, spatial, and chromatic stability. It's a very versatile light source with flicker functionality. And so I would like to thank you for listening to me, and thank you very much on the bottom of the sources for the images. This is it for me today. Thank you very much.